Okie doke. So far, we have talked in the first 2 weeks of this class about principal components analysis, exploratory factor analysis, but then under this big heading of factor analysis, we have the last one called confirmatory factor analysis. So here is kind of our big picture. We'll talk about path diagrams, the model equations that are specific for CFA, and something that I briefly mentioned last week about model identification, that's definitely more important today as we step into CFA. And then we won't do anything by hand for CFA because it gets more mathematical and the estimations and things as we've progressed along. But we will let R do CFA for us. And so I'll take a little bit of time and introduce you to that software and show you how to use it on this computer with R. I do believe all the computers in 103 have R, but it's really easy to put it on your own computer and work from there as well. So factor analysis, all of factor analysis really, whether it be EFA or CFA, here, it was a good quote that I found. It says, factor analysis is like a pair of magical glasses that allows the researcher to see the causes when viewing the measured variables. So kind of another analogy, last week I gave the analogy about looking at the bridge from different perspectives. The bridge never changes, but the way that we look at it and what we uncover by that perspective might change. And this one is kind of the same depending on the glasses that we put on. Might not be magical glasses, but if we don't have good eyesight and we put actual glasses on, then we can see and everything becomes clear. But sometimes we put sunglasses on, sometimes colored glasses, and so it really just changes the way that we see something. So we did a lot of comparison last week between PCA and EFA, and now we'll add kind of another column to that and distinguish EFA from CFA. So EFA seeks to determine the smallest number of factors that can adequately represent the original data, whereas confirmatory seeks to confirm or reject an a priori hypothesized factor structure and to measure the relationship between each factor. So in EFA, you just kind of throw the data in and see what it produces, and you can put some constraints about the eigenvector values or the number, but typically we just see what we can uncover from the data, whereas confirmatory, we have an a priori hypothesized structure, and we input that specific structure and see how well the data fit what we hypothesize it to do. It is EFA is descriptive exploratory, whereas confirmatory factor analysis is a confirmatory procedure. Just like in, if you were doing a one-way ANOVA, you would have a null hypothesis that there is no relationship among the groups or difference among the group means, and an alternative hypothesis that at least one group mean differs. And what we're trying to do is see how well we can test the different group means and put a level of probability that yes, they are, or no, they are not different. So we're confirming what our hypotheses said. EFA is not driven by prior theory, but CFA requires a strong theoretical foundation. There's a lot of background that goes into CFA. EFA, we might do that when they're, when the instrument is very new and there's no research on it because you just wrote the items and collected the first set of data ever. So there was no, you have a theory of how you designed it, but you're really just exploring it. Whereas there's a theoretical foundation. That data hopefully has been explored and exhausted in the past, and what you're doing is confirming. In EFA, there's no pre-specified structure of the linear relationship, but in CFA, there is that pre-specified.
if you were looking at a already developed scale, but on a new sample, would you do a CFA?
If the new sample was similar to the old sample, and so you were doing, using one that was supposed to be applied to undergraduate college students, and if you applied it to undergraduate college students, then you would most likely just want to confirm that it fits like it has fit previously for that group. But if you were wanting to use it for graduate students, you might want to explore it and see how it fits, what it was intended to do. But since you have a different demographic of who it was supposed to be applied to, then an EFA would probably be more appropriate in that case.
I'm thinking because in my lab we use a lot of like mother-infant bonding scales, but we're using that with fathers as well. And a lot of them haven't been looked at in a father population, so that would be an EFA.
So that would probably be an EFA. And there are a few researchers, I would say, that are more favorable towards CFA, even in an EFA, like we would do an EFA there, or most likely would do an EFA. But a person who is more statistically minded might almost always do a CFA, and it kind of goes back to the quote from Templin that says, it's not the data's job to tell you what it does. It's your responsibility as a researcher to have some background, to have some theory, and then go along with that theory. And we have a lot more control, as you'll see whenever we do CFA, to specify different things in it. And so in some cases, it's not necessarily bad to do a CFA if you do have some prior theory. So what you might want to do in that case, if you have a large enough sample, is to split it and did half of it explore it and see if it really does, and then to confirm it on the other half of the data. And a lot of times you'll see them paired together like that. Again, not on the same exact sample of data, but on maybe split data, like a split half. In EFA, the number of factors can be varied and explored through multiple analyses. But in CFA, the number of factors is pre-specified prior to the single analysis. And I say this one a little bit with hesitation because we are going to see a few examples and suggestions from really, I would say, experts in the field of measuring latent constructs, where we do more than one CFA and we can compare them, because CFA is going to provide us with some model fit indices that we can compare different model fits. EFA didn't really do that. It was still subjective. When we compared the 2 to the 3-factor model, we might compare the residuals, we might compare the total variance accounted for, but there wasn't, a number where we said this one is better because this one is this number is higher. CFA gives us that. So sometimes you will see where we do multiple CFAs, again, driven by theory, because they give us some model fit indices. In EFA, we analyze the variance covariance or the correlation matrix, and we talked about the pros and cons of doing one or the other. But in CFA, we always analyze the variance covariance matrix. You'll never see the correlation matrix analyzed for confirmatory. In exploratory, the factor selection is based on subjective criteria. Subjective because somebody might choose a criteria based on Kaiser's rule of an eigenvalue greater than 1. Somebody might look at a screw plot and person A says the bend is here and person B says the bend is here. So it's very subjective. And in CFA, factor and item relationships are pre-specified. In exploratory, simple structure is obtained through rotations. And what is simple structure?
The lowest number of cross-loadings, right?
Yes, the lowest number of cross-loadings where an item loads only on one factor. Simple structure, or any structure for that matter, in a CFA is specified in the model. So you would tell your software program that I want this to be simple structure and I want these items to only load on this factor and I want these other items to only load on this factor, and then it will see how well the data fit that pre-specified model that you've input. In exploratory factor analysis, the unique error variances of the variables are uncorrelated. And in confirmatory, those error variants can be modeled. So we can specify them to be correlated or uncorrelated. And these are some of the software that will do each of these. So we primarily used SPSS for exploratory factor analysis. I also showed you a little bit in R where we could do that. Lizeral, Amos, M+, will all do confirmatory. We're going to use specifically the Levon package in R to do that. So let's jump into the first article. There'll be two for today. This is the first one, exploratory and confirmatory factor analysis of, I forgot what this was called. What scale are they using? Oh, the Wechsler Intelligence Scale, and this one is for children. So here are some guiding questions for your table to discuss as you go through it. And here I say start reading on page 39. You can skim the first few pages if you want to, but the guiding questions are a little longer. No. That's what you can get.
I don't know if we talked about this in the
Can I get your little
intro page?
Okay.
I'm just gonna do this one rewriting one.
Your opener question here.
It knows also stable dots, but it's one of my originals. I don't know. Okay, that's what EFA, the first one. You're starting the first one is students, and then CFA, we compare what we want.
Right now. I'm good, but thank you.
More steps. What data was on? And this is more than one. Or was the difference before and color? It's just bad. Okay, so basically, yeah. I think these are like the data. These are they can't put off those data and more than one day. Others are super sad. Oh my God. I wasn't trying to imitate.
What method of extraction and rotation are you
how you factor it. No, I mean, that's consideration. Okay. What is the same? We also have, I haven't done screen test. Okay. You need to confirm that those tests were held, yeah. I need to confirm that, like, they want to be able to. I assume whatever one is for confounded thing. Yeah. Our criteria is these two days. The item value will but the value for the contraction is $0.999. The test is the same the minimum of 30. Thus, the PA results suggested with your report calculates the accuracy of the state two. Consequently, electing two group of it. That what you said? Plus, I like that. What is the EFA solution? Simple or complex? Sure. No, that didn't sense. Overall, the factors that emerged across the solutions. I noticed that clear cut. Variables tend to have only one primary one exception. The subtest also will find a factor composite, which needs to be the measurement model. Exception is picture conjugates. With one complex, I guess, right? It's hard to know what the indicators for you. How big is the sample? Oh, that's not that big. How was New York chosen? They used BFI. Yeah, that would be one more. What do you think? Okay, yeah, okay, BFI, the REMS, and compared to the CFI, the REMS, and what was the inclusion of simple or complex? The AFC. Oh, really? And the password is just one. That's true. When you say I would say that. Okay. There's no proximity, but there is. Oh, one who doesn't know that. I think that's when we show them and we look at it and you have to. That's picture span. No, picture span is one. When it goes like. Isn't it like the pattern? I don't remember.
Picture straight is where you like show them 2 seconds.
Yeah, that's where
You
you
flip it over and then they can do actually.
Yeah.
That's why we were like,
That's not
one factor U, 2-factor EFA, 3-factor, 4-factor first order, 4-factor second order.
Is your span, you know?
I think it's a
Supplement.
supplement.
Oh, oops. The question is, how do you get solutions on simple or complex structure, and I don't know. Look at the structure.
They mostly low. Everything mostly low.
Yeah, it's, not
I said mostly. I feel like I don't know if it's simple because that seems to be a strike definition, but also like I want to call it complex because there's no example.
I'll put a little approximately.
What other
Modification pieces instead right in the table.
Yeah, I think it's interesting we can't remember what picture comes up.
You just gave it.
In February. November of 2016. It might have been right. Final models choice.
I get pictures and I get pictures, not thousand pictures.
I just want to say that Jesus.
I'm gonna give you 5 more minutes.
So I'm like, maybe they did throw it out.
Maybe that's why I'm using this. No, I don't think that's it. Is it 10?
Oh, this is like a tour.
Oh,
Now we're fine.
yeah, because it's had like trails and stuff, right? The days or whatever. What's his name? That's Isn't she? I'm pretty sure it's like from names. No, I'm pretty sure it's what we did in personality, but we have to like. We did this really hard. We had to go from it was like half the dots, but you would have to number to letter. So hard. Yeah, his name Kevin. Yeah, he was. I asked for the number of it. I need to wait like 4 days. It's like.
So it'll probably 5.7 class. Solutions. What about just kidding.
I think it's even more graphs than we did in vehicle.
It's all the way. I'm just doing a lot. Oh, those are the miles.
Just. Oh, no, but maybe.
Yeah.
Oh, it's like the one where they pick the thing that doesn't fall off. So they get like,
I remember.
it's like,
Off. This is not.
Yeah.
No, I don't know that it is, because I could, that's.
No, that one's it.
Maybe the test.
Which you told me there's a person, parents that will try to secretly get what's what it is so that their kid can get into it. So, take the photo and then yeah, it's a big one. Yeah.
I know people
What's he calling?
It was such a bad impression. Yeah, really bad. Maybe.
Oh, I'm shooting kids in time. I can as much time as I can. And I'm not the last one, so maybe I don't finish. And have it. So I was a chaplain to I was like, I just want to finish this shit. I just like that. Try to leave it in.
Okay, so this was an example of an article that used both CFA and EFA. Why did they mention that they did both?
To explore potential factors and compare resulting models with an independent sample.
Mm-hmm. And why did they do EFA first? Why not just jump into CFA?
The first time
Good. It was used on a special population, so they wanted to explore it first on that unique population and then confirm it in another set of analyses. Did they use the same sample in both? No. How did they distinguish their samples?
What was the question?
How did they distinguish their two samples? How do we know it was different?
By year.
By year. One of them was in 2007 and one was in 2008. What data were actually analyzed?
The risk for scores.
The scores. So this is an example kind of different than how we've talked about before. Usually we would take a bunch of items and see how they grouped so that intelligence, it's already suspected to have these 10 underlying factors. Let me see if I can find it. So if you look on page 542, there were 10 subtests of this intelligence scale. So they weren't taking the item responses and seeing if they fit into these 10 scales. They were actually taking their item responses and creating those subtest scores and then running the EFA and CFA on the 10 subtest scores to see if the subtests grouped into specific factors themselves. So that's a different way of using the factor analysis, not just on item response scores, but here on the actual, or not on item responses, but on the actual item response subscores to see if the subscores tended to group into, so they're kind of making this hierarchy of the test itself. What method of extraction and rotation were used for EFA? Good. Principal axis factoring. The direct oblimin oblique transformation. Good. And how was the number of factors chosen there? A lot of ways. Yeah, there was a different one. The minimum average partial procedure. That's another one that we didn't talk about in class. We talked about parallel analysis and the Kaiser rule. How many, the next question is, was the EFA solution simple or complex? Mostly simple. Which ones did they compare? Which fits?
2, 3, and 4.
2, 3, and 4. They do a really good job of giving a lot of detail in a very condensed manner, I felt like. So we get the different loadings. We get all 3 of them. Of course, they only had 10 items. But we get a lot of detail about how they did the procedure, what procedure they did. They even mentioned I used the correlation matrix. That only took, part of a sentence to put that in, but it gives us more information as the researcher who now know what that actually means in terms of what they're analyzing. Then question 7 in the CFA, what model fit indices were used? The CFI, Yeah, REMS, RMSE, AIC, good. And the chi-square, yes. So we will talk about all of those different measures. And in the CFA, what models did they compare? So the 2-factor, 3-factor,
4-factor first order,
and 4-factor first order and second order. So this is another case where they didn't just do a one and done CFA. Sometimes you'll see, do this EFA, explore the 2, 3, and 4. Okay, this one fit. Now let's confirm that single one. But they let some other theory guide those CFA models. And so there was also a comparison there. And then they could compare what the CFA said compared to what the EFA said. When doing CFA, what other indices, in addition to overall model fit, should be examined? What do they mention there?
Indices and residuals, basically the standardized residuals. Here we go.
Yeah, standardized residuals, and we will talk about those and see what those are. And what final model was chosen for the CFA? 4-factor first order. And what about the EFA? 4-factor. And we don't really have levels of ordering in EFA, but so they showed consistency in their different models that they explored and confirmed. I like that article. I think it was pretty good. Pretty easy to read. Y'all like that one? Good. So don't forget, next few days, find your own. It can use EFA or not, but it must use some type of CFA in a research field that you're interested in. So procedures or process for CFA, the first one is to specify the measurement model. Specifying the measurement model includes the number of factors, so maybe it's a 2 or a 3, the relationship of each item or variable with each factor. Each factor requires at least one item. We also specify the relationship among the factors and the type of identification. So there's a lot of things on the front end. That's why it's so important that CFA be driven by theory, because theory must specify and guide why you're choosing the number of factors, how each item or variable corresponds to each factor. Even the relationship among the factors. So, with the rotation, we kind of explore, are these factors correlated or not? And we have to know, because we have to specify that in the very first step of doing a CFA. The next one is to use software to evaluate the fit of the model with the actual data. So the software calculates true variances and covariances among the variables, which is what EFA does. We look at that either covariance, variance matrix, or the correlation. And then, so it calculates some known things, and then unknown parameters are estimated. So those are the factor loadings, the factor correlations, the error variances. So we specified it, and then it estimates it based on the data. The estimated parameters are used to reproduce the variance covariance matrix. Well, that sounds kind of familiar to what we're used to. That's what EFA and PCA do. They reproduce that correlation matrix, but without any specification on the front end from us. And then, this is kind of the kicker. Before, we just looked at the reproduced and the original. We talked about, well, couldn't we just do a chi-square and see how different they are? And the ML procedure actually does that. But all of the CFAs do significant statistics are calculated for the item parameters for inferential purposes. And the reproduced and observed matrices are compared. So that is how the model fit statistics are produced, by comparing what actually the variance and covariances are among the variables compared to what we specified in terms of the relationship and the structure from step 1, how well the estimated item parameters reproduce that variance covariance matrix. Then we can evaluate the model fit statistics. So some of these were used in that other article that we just read, the CFI, AIC, RMSE, RMSEA in this case. But then there's also different software will give different indices. Sometimes you want high, sometimes you want low. And we'll talk about how we interpret all those different ones. And then examine the residual covariance matrix. So what is the residual matrix?
The error matrix.
Between between
the reproduced and the expected.
Good. So down here, when the observed and reproduced matrices are compared, it gives us a residual matrix, and we can look at the values there. We vaguely kind of tiptoed into this for EFA, but it's actually a procedure and a little bit more guided here in the CFA. And then it can also be used for cleaning the model, removing poorly fit items and things like that. So it can be used as a technique for cleaning up a scale, and we'll talk about a way to do that tomorrow. So in most statistics, we use what we know to estimate what we don't know. In factor analysis, the goal is to estimate what you don't know from what you do know in order to build a model of the relationship from what you don't know to what you do know. So in EFA, all we have is the data. We don't really know what the underlying causal structure is, and that's what we're trying to see. And so we're using what we know about the variance covariance, the relationship, to estimate what we don't know. And here we saw that there was this causal influence from what we don't know to what we do know, and that's what we were trying to look at. We'll use those same path diagrams even more. They're really fundamental for CFA. And so when we do these, the circles and ovals, just like last time, but I'll get a little bit more specific. The circles and ovals are unobservable. These are latent variables or factors, and we call them exogenous variables. You heard that term before? What class did you hear that in? SEM? Regression, maybe SEM. So has anybody had SEM? Oh, some of y'all have, wow. So CFA is just a component of SEM. Exogenous variables are those whose values are independent from the state of other variables in the model. and which have a causal influence on some other variables. So we think here that the unknown factors or latent traits are causing these observations in the items or variables. Squares or rectangles are observable, and these are endogenous. And those whose values are determined by the state of the other variables. So when we talk about the exogenous variables, they have a causal influence on something. So we see that happening here. And the squares and rectangles are endogenous, and so they're receiving that cause in what we're actually observing. We see these unidirectional arrows, and these are regressions or residuals. So that is the direction of the causal influence from the factor to the observed variables, or from the error to the variable itself. And then sometimes we see bidirectional arrows that represent the correlations or covariances. Typically, you'll see that here, and this would be the correlation or covariance between the unknown factors. We explored that with an oblique rotation in EFA. We fixed that component of the path diagram to be 0 when we did an orthogonal rotation. So more on the path diagram, the details. The loadings capture the direct causal effect between the factors and measured variable. And so these are going to be lambdas, and the subscript of lambda is the to variable and then the from variable. So lambda item comma factor. So notice this one here, lambda 1, 1 is for item 1 factor 1. Here, lambda 3, 1 is 2 item 3 from factor 1. So that's how we'll specify and denote our factor loadings. The first subscript will be the item. The second subscript will be the factor. The next piece of this, as exogenous variables, factors have variances and covariances. So the variance is here. No, it's not. Variance is on a single factor. So here, how does factor 1 vary? So that's what this path specifies. And it's denoted C11, to and from, but it's going from itself and to itself, so we just have C11. Whereas for factor 2, the variance is C22, from factor 2 to factor 2. The covariance is between two different factors. So this is the go-between, from and to. So here you see C12, that's going to be equivalent for us to C21. Going from 1 to 2, and it's also going from 2 to 1. Okay, the next piece is the errors down at the bottom. So as exogenous variables, the errors also have variances and sometimes covariances. So they always have a variance on the error term. So that is this piece here. I'll keep it blue. So variance of E1, variance of E2, variance of E3. And notice that we use theta to represent the variance of the different error components. Sometimes we allow covariances between two different error terms. And that's when you see the subscript 3, 4 or 4, 3. When there's a different number there, that means it's a covariance between two of the error terms. When it's the same value, like theta 1, 1, theta 2, 2, that's the variance on a single error term. And you might just note that we didn't have these covariances in EFA. In EFA, we had error. We had like the dirt on the little vegetable and fruit image, but we didn't allow the dirt or the error among the different pieces of produce to covary. Right here, we may allow that covariance. And paths from the error to the observed variables are assumed to be 1. So here, this path from error 1 to variable 1 is 1, and 1, 1, 1, 1, 1. So in terms of the different paths and parameters, we have direct paths which go from a factor to an item, and those are here in red. And notice there's only one arrow on them, so they're directional. We have variances of a single exogenous variable. So here's a variance, a variance, a variance, a variance. And these are all unknown things. We don't know the lambdas. We don't know the values of those direct paths. We don't know the variances of the factors because we don't see the factors themselves. And then we have covariances between two exogenous variables. So maybe the errors or maybe the factors themselves. So how do we model? That's the picture. So if you're visual, I'm visual. I like to see the picture. We're trying to model this set of equations. It's kind of similar. So let's just recap. When we did PCA, principal components analysis, what was the dependent variable? Was it a factor or an item? The factor. And we use a linear, 50-50. We have a linear combination of the factors that we don't know or components to predict or build each of the different components. But then in EFA, what was the dependent variable? The item. And the models were linear combinations of the factors themselves. The unknowns were the independent variables, and the dependent variable was the item. It's a similar structure in CFA. So this is going to be an M factor model. So if it's a 2-factor model, M is 2. If it's a 3-factor model, M is 3. For an individual, expresses the variation and covariation in a set of observed continuous variables, so those are the V's, as a function of the factors F and residuals. So there, in terms of observed variables, there's a total of P observed variables or items, we've seen that. And then there are M unknown factors. So the details, P is the number of items and M is the number of factors. So what are you going to think? Should P and M be equal, less than, or greater than?
P should be greater than.
Okay, P should be greater than M. The number of items should be greater than the number of factors. Good. Capital V is the observation from person I on continuous variable J. And we're in the social sciences, typically counseling, psychology, education. And so throughout this class, I've used persons. I was giving a research presentation on Friday, and it was like scientists dealing with medicine and somebody talking about fish and streams. And so it was really hard because maybe you want to do CFA with data, and if you don't have people, you have fish, or you have plants, or something like that. So we can try to keep an open mind about those things, but typically I think for the social scientists, people make sense there. But do know that if you're in a different field, that could vary. Okay, little v is the mean of variable j, or the intercept of the model. So we notice the little v's here. So this is the mean of item 1, the mean of item 2, the mean of item up to item p. Lambda is the loading, and specifically lambda jk. So this is the loading of variable j on factor k. And if we're talking about the factor, capital F, F sub ik is the factor score, S-C-O-R-E, of person I. So each lambda has an associated factor, lambda factor. And the first subscript of the lambda is the item, and the second subscript is the factor. So notice that the second subscript of the lambda and the F is the same. So each lambda has an F, and that subscript should match for those. We can assume that each factor score has a normal distribution with a known mean and standard deviation. So we might say that the distribution of F is normally distributed with a mean mu sub Fik and standard deviation or variance sigma squared sub Fik. Typically, we will set that the mean of the factors is 0. Sometimes we'll even standardize them, but not always. And then the epsilon is the unique variance, or maybe the error. I feel like that's, maybe a psychologist could do a study on, if you talk about someone, what is your error in terms of your normality, or what is your uniqueness and how that comes across. So we'll talk about epsilon in terms of uniqueness, but it's also the error for that person on a specific variable. So you might think of it also as the residual if you're thinking of regression. Here we can assume that the epsilons are also normally distributed with a mean of 0 and a standard deviation of u squared, where u squared is the uniqueness of that variable. So we're using some similar terms even as what we did in EFA. And an item's error term is uncorrelated with the factor scores. What does that mean? So this last little note here, I'll use this gray pen. So here, when I say an item's error score is unrelated, so this error of E1 is unrelated to anything about the factor itself. So there's nothing that goes from error to factor in a path diagram. They're assumed to be uncorrelated. So we think about having all these items and these item or variable scores. We need to put this in a matrix form, and we would do that this way. So capital V is a vector of responses. Little v is a vector of variable means or intercepts. Lambdas, this is capital lambda that's filled with little lambdas, is a matrix of factor loadings or factor patterns for the variables. Capital F is a vector of factor scores. And then epsilon is a vector of residuals.
What is lower than?
So F is a matrix, so capital F itself is the matrix as a whole, and then the little components within it, the factor scores, are little f. We talked mostly in EFA about how the correlation matrix was really the foundation of everything that we did and what we analyzed. For us in CFA, the variance-covariance matrix is the foundation. So here, when we talk about the covariance of V, that's the covariance of the observed variables, or that matrix of observed variables, denoted capital sigma. And here is the relationship of how we're doing this reproduction of the variance-covariance matrix. We're taking the factor loading times factor loading transpose, but there's something in the middle there, that phi. So phi is a matrix, square matrix, of common factor covariance. And the theta is also a square matrix, a diagonal covariance matrix for the residuals. If I go back to this one, remember we talked about the variance and the covariances of the errors being thetas. That's what that theta is here when we're trying to reproduce the covariance matrix. So let's think about the one-factor model. The one-factor model with 3 items, and that it's a very simple one, but that would be our structure over there in matrix form. Here we have the vector of observations, and so think of each person in here, all 13 of you kind of have your own V1, V2, V3 score, and you have a mean of everybody on those 3 items, and then the loadings, the factor scores, and the errors are from, if we put everybody's responses to those 3 items in a big spreadsheet and then tried to fit everybody to the same model, how could we do that best? So when we talk about the covariance matrix or variance covariance matrix, the structure of any variance covariance matrix looks like this, where we have what on the diagonal? What is that? The variance, The variance of item 1, of item 2, and of item 3. And then in the off diagonal, what are these values here? Covariances, yes. B is the covariance matrix of the factors. So if I go back here to this one, when I talk about phi in this case as the variance covariance of the F's, because I have 2 factors in this one, we would have the variance of F1, C11, the variance of F2, C22, and the covariance, 2,1, between the two. So because it's a two-factor model, phi is a 2 by 2. But in this little example here, where I only have one factor, there's nothing for it to covary with, and there's no really dimension of the factors, plural. So because there's just one, this is actually just the variance of that single factor. So in a one-factor model, phi is really just a single value, which is the variance of that factor. And then theta is the diagonal covariance matrix of the residuals. And we see the variance of each of those different error terms there, assuming that the errors are uncorrelated. So in our diagram over here, I don't see anything going from E1 to E2 or E2 to E3. We are assuming those to be 0. You with me? Okay. So just some statistical rules when we're dealing again with matrices and different things. Let X and Y be unknown, and A and B be two known values. So the variance of a constant equals 0. So we could even say, somebody pick a number. 6. Let's say that A equals 6. Then the variance of 6 equals 0. The variance of any single value equals 0 because it doesn't vary, it's 6. You said it was 6, it's 6. The variance of a constant multiplied by an unknown equals the value of the constant squared multiplied by the variance of the unknown. So if I'm trying to figure out what is the variance of AX, this might be the variance of 6x. That's our equation, 6x, because A equals 6. Then that equals, we take the scalar out of whatever's inside and square it. 6 squared, that's not pretty, times whatever the variance of X is. Then the variance of the sum of two quantities is the sum of the variances of each quantity plus 2 times the covariance between the two. So I'll do it with A's and B's first, and then I'll put in some numbers and show you what happens. So here, the variance of AX plus B is the sum of the variances of each of the quantities. So the variance of AX plus the variance of B plus 2 times the covariance between A, X, and B. And even here, we can simplify it a little bit further. The variance of AX is what? A squared times the variance of X plus, what is the variance of B? If B is a known value, 0, plus, and then if we think about the covariance, so we have some quantity, maybe 6x, and x can vary. X is an unknown, but b is fixed. So let's say we have 6x over here, and that can vary depending on what x is, but then we have b, which is fixed. So the way that the unknown can vary with the known, there's no way for it to, because there's no co-varying. Yes, one of them varies, but it can't co-vary because the other one never changes. Does that make sense? Okay, so the covariance of an unknown with a known is also 0. So the last piece of this, 2 times the covariance of AX with B is what? 0. So then we could just simplify this into a square variance of X. If I have 2 unknowns, what do you think this will be? The variance of X plus Y will be what?
Variance of X.
Variance of X plus variance of Y plus, good, 2 times the covariance of X and Y. And can I simplify anything there? I can't. If X is unknown, then X could vary because X could be 1, 2, 3, 4, 5. I can vary Y, so everybody has their own Y score, and we can calculate a variance of that. And because X varies for everybody and Y varies for everybody, then we can calculate a covariance between those two. So we can't simplify any further. The last one is calculating the variance of 2 unknown values with a scalar. So here, let's just break it apart like we have up there. We'll have the variance of AX plus the variance of BY plus 2 times the covariance of AX with BY. So what can we simplify the variance of AX to? Good. A squared times the variance of X plus B squared times the variance of Y plus, now if we think about all the X's and multiplying them by A and all the Y's multiplied by B, looking at the covariance of AX with BY is actually the same thing as looking at the covariance of X and Y by itself, and just that quantity multiplied by 2 times A and times B. So we can take the scalars out of both of those quantities and just look at the covariance of the unknowns. So these are rules that we're going to use in a little bit more with lambdas and variances and covariances of factors. So let's try here. Let's try to estimate the variance of the observed variable V1. And we know that V1 equals the average of all V's, so the mean, plus the factor loading of lambda 1, the factor score of factor 1, and the error term E1. So let's calculate the variance of V1. We'll just start out and say, then what is variance? VI1. That's going to equal the variance of V1 plus lambda 1 FI1 plus epsilon I1. So what's the first thing that I could do for this? And here's our rules if we need to remember. So I'm trying to simplify this, so it's really just some algebra. Simplify it into its most simple form. What's the first step? The variance of the sum of quantities is what? What did we do back here? When we had maybe variance of AX plus B, we said the variance of the first plus the variance of the second, and then we had 2 times the covariance. Variance plus co. Variance plus co. So what are we going to do over here? Break it up, okay? So we'll have the variance of the B's plus the variance of the lambda 1 F I1 plus the variance of the error. But we needed that covariance component, but we said that the covariance of anything with a known is what? 0. And are any of those pieces known? The V1, the little v1 is known. So is there a covariance component of this? No. And if we just look over here at the piece itself, V1, so we're looking at, we'll say that it has its own mean, V1. And then we have this piece here, the lambda, and then we have the error term here. And we don't see any pieces that go and covary just with V1 because it's a single variable. So V1 can't covary with another variable right now. Okay, let's simplify even further. So V is an average. So the variance of the average is what? So I'm going to use this rule right here. If the average of a number is a fixed number, what is the variance of that? 0, okay? Plus the variance of, okay, let me step back for a minute because I think that you're not with me. Okay, is that an accurate observation?
Can you turn the lights on too?
Yeah, I'll turn the lights on. We got to get serious here. It is cloudy today. Okay, so let's kind of try to put this in an application, okay? Let's say that so everybody, I'm taking a survey and it has 3 items, okay? And so everybody has a score on the 3 items. So here, this is your score, or no, we won't even use score. Your response to items 1, 2, and 3, okay? So on a piece of paper, what is your score? On a scale of 1 to 5, what is your score on item 1? Write it down. And what is your score to item 2? And then what is your score on item 3? Okay, this was a scale of 1 to 5. Okay, so we know that we could take everybody's score on items 1, 2, and 3. So if I put everybody together, then person 1, person 2, up to, there are 13 people. It might look like this, 1, 3, 8, 2, not an 8, because we had a 5 scale. 1, 3, 4, 2, 5, 5, and then maybe the last person was 3, 2, 1, okay? So we could take everybody's score on the first item and I could average it, and I'll just say the average was 2. So little v1 equals 2. Little v2 equals 3. And little v3 equals 4. Okay? So your item responses vary from the person next to you, but everybody has the same average to that item, if I'm thinking of this class of 13. So what we are trying to do in CFA, in this one factor model, is figure out, okay, what is the relationship between the unknown factor that we're trying to measure here with everybody's unique item response. And so this lambda that we estimate, that is the relationship from the factor to each item, this lambda value will be the same for all people. And notice the subscripts of lambda. There's not a subscript that specifies the person. So there's a lambda item 1 factor 1, a lambda item 2 factor 2, and a lambda item 3 factor 1. Whereas up here I have factor 1, but if I go back into the model details, notice the factor is I1. So it's I is the individual. So I'll put that here. I. So I think everybody has a unique, everyone has a unique factor score. And because everybody has a unique factor score, so this is unique, but for everyone, the average of all the items is the same, and the relationship between the item and the factor score is the same. You're not going to reproduce your actual item response exactly, are you? No, unless this was a perfect model, but it's not. So because of that, everybody has an error that is the difference between what is common between everybody and your calculated factor score and what is left over. So these are also the unique for each item and person. And if we go back to the equations, one before that, that's why sometimes subscripts are important. If we can look at those to help us understand what's the same for everybody, every person, what's the same for every item. If it has a 1 or a 2, it's the same, but if it has an I or a J, it differs. Okay. Okay, so what we're trying to do here is remember the covariance variance matrix of this part right here, or what is the variance covariance matrix of all of these items. Now, we could calculate it. We could take it, calculate the variance covariance matrix of the items. And so we would know exactly what the variances are. But what we're trying to do is not just take the data and calculate, well, what is the variance among B1, B2, B3, or variance of B1 and B2 and of B3, but we are on the last part of the CFA. So we've already calculated the real one. Let's say in our minds, maybe we've already calculated the lambdas and the factor scores, and I'm trying to reproduce the variances of the item. So I'm trying to reproduce that variance covariance matrix. That's the step I'm in right now. So how could I reproduce the variance covariance matrix using the different CFA components? Not the data, but the CFA components, because that's the reproducing part. You with me a little bit better? Okay. So let's start over. And we need to use our different rules down here for variances, because I haven't put in the actual numbers here. So that's what's making it a little bit hard. We're still just dealing with parameters. But think over here, okay, the items are actual numbers in the data set. And so I can calculate and observe an average, a mean for those. And I can use that. I'm not trying to reproduce the means. I can just use what I've already observed from the mean. But I don't know the lambdas, I don't know the factor scores, and I don't know the errors. So we need to know if they vary, if they're unknowns or if they're knowns or fixed. Okay, so back to, so how do we reproduce maybe the variance of the observed variable using CSA parameters? So how are we going to reproduce the variance of VI1? You already told me, just take the variance of everything on the right-hand side of the equation. So the variance of the item means of the variable 1 plus lambda 1, 1, Fi1 plus Ei1. And then what do all of these rules of the variance of some components being added together? My rule tells me to take the variance of the individual components and then add 2 times the covariance of them. Okay, so that's what I'll do next. This would be the variance of the first component, V1, plus the variance of the second component, lambda 1, 1, Fi1, plus the variance of the epsilon I1. And we said we know then we add 2 times the covariance of the means, the lambda F, and the epsilon. I'll kind of put it like that. That's not a technical term to write that, but just kind of stay with me here. Because the average or the item mean is fixed for everybody. So yes, you have your own item responses, but the average of the item response is the same for everybody. That means when I try to covary something with it, it's not going to covary because it's fixed. It's stubborn. Okay, so this piece will go to 0. Okay, so now let's look at those 3 pieces of variance individually. The variance of the average score. What will that be? Is the average score different for everybody? No, so the variability will be 0. Good. So this piece will be 0 plus, now is the lambda, is the factor loading or the relationship between the factor and that specific item the same for everybody? Yes. Is the factor score the same for everybody? No. So the lambda is fixed and the factor score will have some measure of variance. So that puts me to this option here, the variance of a fixed number with a non-fixed number. So what will that piece be?
Lambda squared times the variance of that.
Great, yes. Lambda 1 squared times the variance of f. Very good. And then does everybody have their own error term for the item? Yeah. So we'll just leave that as the variance of epsilon I1. Good. Now, we need to know, well, what is the variance of Fi1? We're trying to estimate it with our CFA model, but we're estimating that the variance in the path diagram, what is the variance of F1 on the path diagram? C11, And what is the variance of the epsilon 1 in the path diagram? Theta 11. Good. So input those things. So they're still unknown, but they at least have a parameter of their own. So lambda 11 squared times C11 plus theta 11. The end. I used to have a professor who would say, you know, put the box around it. Did y'all ever do that? And then when he was like really, really done, he would put RIP. This one is resting in peace. I hope that you have some peace. I'm not feeling it, but that's okay. Okay. What we're trying to do is we're trying to figure out the mathematical side of how does CFA reproduce the variance covariance matrix of my observed variables, but using the CFA parameters that we see there on the path diagram, okay? This is reproducing the variance of those variables V1, V2, V3. Now, how can we also reproduce the covariance between V1, V2, and V3? So first, we need some rules. Rules of covariance. We've already kind of figured out some of them. But the covariance of a constant with another variable equals what? 0. Good. Think about this one. The covariance of an unknown variable with itself equals what? The variance. Yeah, look at the path diagram. So a variance and a covariance path has a double arrowed line. That's how we view variance and covariance. Variance typically goes from one variable to itself. Covariance goes between two. But if we view this double arrow right here as being a covariance, It's like the covariance of F1 with itself, which is actually just the variance of that factor. So we'll say the variance of an unknown variable with itself equals the variance of that variable, or the covariance of xx equals the variance just of x. If a scalar is one of the unknown quantities, it can be multiplied by the covariance, be multiplied by the covariance between the variables. So when there was a scalar variable in a variance and we took it out, what did we have to do to it? We had to square it. But this time, it's not necessarily like if this was on the AX and AY, we would take it out and it would be squared. But because it's only on one of the quantities, it's just A times the covariance of XY. So just take it out. That scalar inside the covariance of, on one can be multiplied by the covariance of the two unknowns. And lastly, the covariance of the sum of two unknown variables, this is not supposed to be there, with another unknown is the covariance of each of the unknowns being added together with the one that is alone. So think of it almost like algebra and distributing something. So if I distribute the z to the x and to the y, I would have the covariance of xz plus the covariance of yz. That one's kind of hard to put into words, so the words might be confusing on that one. Okay, so let these sink in because we're going to take that path diagram like we did before, and instead of reproducing the variance, we're going to reproduce the covariance. Yes.
Can we take a break?
You want to take a break? Okay, yes, we'll take a break. How about a 9-minute break and we'll come back at 10:20.
To make your own. I have my friend
just feel like if I'm somewhere in New York, so I feel like I'm not there, I'm not like ever.
It's a nice little
So
mixture.
I was like, I
don't
would draw your screen. I get out try to draw on your screen. It's not. It's kind of funny. Yeah, it's just a free pen. I got that. How different is our friend? But I think yeah.
It's pretty different.
Pretty different. Like all the coding and everything.
I just learned how to code stuff.
I say that. It's, you know how.
The output is similar because I mean, you have to have all your indices and you have to have.
Right.
Yeah, and Cheney had to open his big mouth. And I had talked to Dad about moving the class to days, and then Cheney was like, oh, she can't.
Okay, so we will talk about now estimating the covariances. Let me just review the path diagram though, and what it is that we're dealing with to try to understand the application of CFA. So when I talk about the V's, those are the item responses. So maybe you have an item response to item 1, item 2, and item 3. And so from that matrix of item responses, capital V's, then we know little v1, little v2, and little v3 are the means of items. Your item responses, 1, 2, and 3. And from that, we can calculate the S1 squared, S2 squared, and S3 squared. And what are those? Variances, variances of the item. And then we can also calculate S12, S13, and S23. And what are those? Covariances of the observed variables. And so these might put together and make a variance covariance matrix, which would have the variances on the diagonal and the covariances on the off diagonal. So that's not very pretty, but you get what we're doing. Okay, so this is actually known but we're trying to reproduce it with estimates of the CFA model specified. So we have specified over here a single factor model. We think that these 3 factors should all correspond to the same factor. So when we talk about that, each of these, I'll go ahead and put VI3. So you are I. So I have I1, I2, I3. There are 13 different I's in this class. And if we try to reproduce the item response from each of those and correspondingly the variance covariance of those, then we use the mean of the 3. So starting with something that we know, but then each of the items has a factor loading on that first factor. Each person has a factor score. Oh, sorry. Those are 3's. So this would be the loading of item 3 on factor 1 and the factor score of person I on factor 1. And then every item, because I'm not going to be able to take the factor loading and your factor score and exactly calculate your item response, there will be an individual error for item 1, 2, and 3. So we have to specify a few things in our model. These lambdas are the factor loadings. F is the unknown factor score. I'll say factor loading. And this C is the variance of the factor scores from all persons. Remember earlier I specified, I'm going to tell you correctly, we said that these factor scores were normally distributed typically with a mean of 0 and a variance of something. So this is the unknown variance. I already assume that they follow a normal distribution, and I'm already assuming that the average of everybody's factor score is 0. But we're allowing the variability of that to be estimated, unknown. So I have factor loading, and then down here we have the individual errors for each item, each of which has a corresponding error variance. And these are the thetas. And back a few slides ago, we assumed that those error variances followed a normal distribution with a mean of 0 and a variance that is the uniqueness. So when we see thetas, we can think about those as being unique. Another constraint that we put on this, though, is that there is no covariance among the errors. Okay? So that's just the overall pass structure. Does that help? Okay, review. Okay, so now we're going to take all of that and these rules that we talked about in terms of co-varying variables, and how do we estimate those? So let's first just think about how can I estimate the covariance between observed variables V1 and V2. So how can I estimate the covariance? It's not on the path, but that's what I'm trying to reproduce, is that covariance line here from V1 to V2. So to start out, let's just do what we did before and say the covariance between VI1 and VI2 equals. And then input in, well, what do we know that the formula for, or the model equation of V1 and the model equation of V2 is? So I'll put in V1, so this is the covariance of little v1 plus lambda 11 Fi1 plus epsilon I1, comma, Vi2 equals little v2 plus lambda 21 Fi1 plus epsilon I2. Okay, the next step is to think about can this first one here, if there is a constant, does it ever covary with anything? No. So the first step, let's just take out the v's, because those are not going to affect the covariance of the overall model. So let's just say covariance of lambda 11 Fi1 plus epsilon I1, comma, lambda 21 Fi1 plus epsilon I2. Okay, let me look at my notes to make sure that I tell you right on this next one. Okay, we're going to use, the next one, we're going to use this rule, where we have components that are added. Well, let me just review mine so that I don't tell you wrong. The first one, the second one, okay. So whenever we did over here, we talked about the distribution of looking at the components being put together when they're added. That's what we're going to do up here. So first we'll think about lambda 1, 1, F1 with lambda 2, 1, F1. And then lambda 1, 1 with the epsilon component. And then E1, 1 with the lambda F and E with E. So there'd be a total of 4 pairings. It's not like, we're not FOILing, so we're not squaring anything by multiplying, but we're just distributing kind of in this summative form. So this will be the, let me go move over some. Okay, covariance of the lambda 1, 1 Fi1 with the lambda 2, 1 Fi1. Okay, so that was the first pairing that we have. And then the covariance of that same lambda 1, 1 Fi1 with the error I2 plus, and then we'll distribute the epsilon I1 to both components of the second part. So the covariance of epsilon I1 with lambda 2, 1 Fi1 plus the covariance of epsilon I1 with epsilon I2. Okay, now we just have to simplify even more. And let's think about what are the fixed values and what tends to vary for the individuals. So I see lambdas, F's, and E's, or epsilon. Are the lambdas the same for everybody? Yes. Are the F's the same for everybody? No. And are the E's the same for everybody? No. So the only kind of scalar component of this is the lambda. And anytime we have a scalar component, we can just take it out and multiply it through. So that's what we'll do in the next step. Is there any scalar in the first piece here? What can I take out? Lambda 1 and lambda 2, okay? So I have lambda 1, 1, lambda 2, 1 times the covariance of Fi1, Fi2. Plus, is there any scalar in that second component? Oh, this is at 1. Is that what y'all are? I hear like chatter, which makes me think I did something wrong. But F1. There we go. Because I only have one factor. There. What can I take out of that second piece? Lambda. Lambda 1, 1, and I have the covariance of Fi1, Ei2. That sounded like bingo, like I wanted to go Ei. Okay, now let's look at the third piece. What can I take out of that? Is there any scalar, any fixed value? What is it? The lambda, okay. So we'll take out lambda 2, 1 and be left with the covariance of epsilon I1 with the factor score. Good. And then the last one, is there anything I can take out of that? No, those actually do vary for both components. So the covariance EI1, EI2. Good. Okay, so now we are to the point where I've simplified it as much as I possibly can, and now I'm going to put in the actual components from the path diagram. So the first piece, I'll come down here, lambda 1, 1, lambda 2, 1, well those are fixed. Covariance of F1 with F1. And what did we say that the covariance of a variable with itself is? The variance of F1. And what is the variance of F1? C11. C11. Good. Very good. Okay. Then the next part, we have plus lambda 1, 1, the covariance of this factor score with epsilon 2. And what did we say about the relationship between the factor score and the error components? It's nothing. So there's a 0. Okay, now we're simplifying. Some things are going to disappear here. Okay, the next one, plus lambda 2, 1. And now I have the covariance of that factor with epsilon 1. Is that going to be 0? And then the last one is the covariance between epsilon 1 and epsilon 2. And what did we say? That was a constraint. There's no covariance between the two error terms. So we did all of this work, and what are we left with? Just that first piece, right? That's all that we are left with. The lambda 1, 1, lambda 2, 1, C1, 1. And think about this. Could we used some statistical rules because I wanted us to see that in the covariance and the variance and the structure when we deal with the matrix. Look over here. I'm trying to estimate the variance between, let me use V1 and V2. So is there any path that will get me from V1 to V2? Oh, lambda 1, 1, C1, 1, lambda 2, 1. And that's all we're left with. So we derived that path using the rules of variance and covariance of what we know and what we don't know, what's fixed and what's not fixed.
Will you put hierarchy?
Yes, we can. Peace. Peace, bring peace. Good. Okay, we could do that for every covariance. We wouldn't have to go through all this algebra stuff because we know what would be the covariance between V1 and V3. What would that covariance be? Lambda 1, 1, C1, 1, lambda 3, 1. We just kind of trace that path. We traced those paths in EFA, and that's how we could see something. But this is the mathematical side of actually what we were doing, even more detail. Okay, so we could take all of those item variances and those item covariances and reproduce. So this is the resulting reproduced variance covariance matrix, where we have the variance components of V1, V2, and V3 on the diagonal, and we have the covariances between pairs of variables on the off diagonal. So from the model equation, the covariance of the data is equal to or equivalent to the matrix of factor loadings, common factor covariance. Oh, no. Got ahead of myself. Lambda is the matrix of factor loading. That's what I was looking for. And lambda transpose. And then phi, we said, is the common factor covariance. So that's this part where the loading is this part, plus the theta matrix, which is the diagonal covariance matrix for the residuals having to do with those different covariances, which are actually just the variances. Okay, so in matrix form down here, the same solution is to take the lambda, and we're just doing the 3-factor here, or the 3-variable 1-factor, lambda transpose. And why did we say that in this instance, phi was only C11? Why is it only one-dimensional, or 1 by 1? There's only one factor. So there's not F2 or F3, which would include more dimensions for variances and covariances among the factors. And then the diagonal theta matrix from the errors there. So even if we do this math and we multiply through, we would see lambda 1, 1 times C1 lambda 1, 1. And there we have lambda 1, 1 squared C1 plus theta 1, 1. There. It's reproduced in yet another way. We could have just taken the original formula and did matrix algebra and not really even tried to do variance of each one, covariance of each one. But all these things are the same. Again, even the math side of it, a little bit, is like looking at the bridge. You can do it one way, you can do it another way. It's all the same. It's just the way in which we look at it. So we can observe the estimate of the observed data. We can observe those variances and covariance from the data, but the factor loadings, the variance of the factors, and the variance of the error components are all unknown. So we're going to get into identification. So how do we identify it? How do I try to estimate all of these unknown things when I only know these little observed variables? So we can go through this process, and we'll do some together, and then you'll do some on your own. Dealing with model identification. So P, in this case, how many variables do we have? 3. When we have 3 known variables, then how do we calculate the number of variances and covariances with that? K will be the number of variances and covariances, and we calculate that using this little formula here. So 3 times 3 plus 1 over 2 equals what? 6. Is that true? Are there 1, 2, 3, 4, 5, 6 variances and covariances? Because we don't, the covariance on the lower diagonal is the same as the covariance on the upper diagonal. That's kind of what we're saying. So there are 6 unique variances and covariances that we know. There is a factor score that is unknown. And then how many unknown model parameters are there? So I don't know 3 of my lambdas. I don't know 1 of my factor covariances, and I also don't know 3 of the error variances. So how many unknown parameters do I have? Add all those up. We have 3 lambdas. We have 1 C. And I have 3 thetas. 7, okay? So then we have 7 unknown values, and I have 6 known unique values. So the number of unknowns is what to the number of knowns? Greater than, less than, or equal to? Greater than, and that's no good. If I have more unknowns than what I know, I'm kind of like spinning like a hamster. I can't go anywhere. I'm trying to estimate things. I don't have enough information to do that. So model identification. A necessary but not sufficient condition for identification is that U is less than or equal to K, where U is the number of unknowns, unknown parameters to be estimated. So this includes the lambdas and the modeled variance and covariances of exogenous variables. So these are the C's and actually the thetas. I should include that. K is the number of unique known variances and covariances from the observed data. So you might even, you might even view this as there are known variances and covariances, and then there are unknown variances and covariances up here, variances and covariances up here. And so we're using the knowns, and then we're using all of these unknowns and trying to bridge a gap between those. So each latent variable so that would be like a factor, must have an assigned unit of measure, either by specifying the scale of the factor, generally to 1. That means fixing the variance of the scale of F and letting the loadings be freely estimated. So when we do this, it's like specifying the factors are normal 0, 1. They are standard normal. Or we could specify a reference variable, typically the first variable, or fixing the scale of the loadings, usually to 1, and let the scale of F freely be estimated. So even more detail, usually fix lambda 1 equal 1. But you could fix lambda 2 to equal 1 or lambda 3, but typically one of the lambdas is fixed to the value of 1. So model identification, there are 3 classifications. We might be under identified, and models cannot be estimated when they are unidentified. So the number of unknowns is greater than the number of known values. And so if we kind of do some algebra here, I go backwards. So the number of knowns is less than the number of unknowns. I don't know enough information. So K minus U is less than 0. And these are the degrees of freedom. So sometimes we talk about models in terms of degrees of freedom. Degrees of freedom are the number of known values minus the number of unknown values. So if the degrees of freedom are less than 0, then our model is said to be unidentified. It is just identified if the number of unknowns equals the number of knowns, but there is no freedom there. The number of degrees of freedom is 0. Just identified models necessarily reproduce the data, but one cannot pinpoint to the adequate fit as evident of model propriety, because such a model would fit any data perfectly. So there's no extra information that we're getting that is specific to this set of data. The last one is only over-identified models. And these are subject to statistical data model fit assessment. The number of unknowns is less than the number of knowns, and the degrees of freedom is greater than 0. I don't think you've ever done anything and it shows the degrees of freedom are -1. Okay, that's like really bad. But we do sometimes see the degrees of freedom is 1 or 2 if we're doing a t-test or a chi-square or something. It's kind of that same idea. We need a little bit of flexibility, but we also need some structure and known situations in order to do this modeling stuff. So option 1, again, 2 options. We can specify the scale of the factor, or we can specify a reference variable. So option 1 is called marker item identification. So if these are the paths, the path diagram, and these are the model equations, this is what I'm trying to model, then marker identification fixes the loading of the first item and variable to equal 1. Lambda 1, 1 equals 1, and you see that here. So V1 is now the reference variable. It could have been lambda 2, it could have been lambda 3. Typically, we just pick the first one. Let's see what happens to the identification when we use this marker item identification method. So here, how many variables are there? 3, okay. And so how many unique variances and covariances are there? 6, Now, how many factor variances are unknown? 6. We'll do the specifics and then we'll add them together, but yes. How many of those are unknown variances of the factor? 1 of them, so that's here. How many error variances are unknown? 3 of them, so we see that here, 1, 2, 3. And now how many loadings are unknown? 2. So we know lambda 1, but we still don't know 2 and 3. So if we add those together, then we do get 6. So here, U equals K, and what are the degrees of freedom? 0. So is this over, just, or under identified? Just identified. Just squeak by. And so, how does that help us out in reproducing the variance-covariance matrix? Well, everywhere that there was a lambda 1, I now have a 1. So it reduces the unknown parameters and better helps us to estimate that variance-covariance matrix. Let's look at option 2. This is called the standardized factor identification, when we fix the variance of the factor equal to 1. So the score of F1 has a mean of 0 and a standard deviation of 2. When we do this, we're actually fixing the whole distribution of F to the standard normal distribution, and we usually really like that standard normal distribution. But in this way, all the factor loadings are still freely estimated. So it doesn't actually change the way that we see those model equations. So what about this one? Again, we still have 3 variables, so we have 6 known parameters. Now, how many unknown variances of factors do we have? None, because we know all of them. How many unknown error variances are there? 3. How many unknown loadings are there? 3. So I have 6 knowns and 6 unknowns. What is the degree of freedom? 0. And so this one is just identified. So the way in which we specify a model via variance of the factor or factor loading, it doesn't change or improve model identification, because in both cases, it's only changing one, but it still, in this case, got us to where we needed to be. Okay, so on slide 31, 32, 33, just do the next 2 at your table. So this one, which has 4 variables and 1 factor, and this one, which has 2 variables and 1 factor. I want you to figure out the degrees of freedom and whether they are over, just, or under identified. So work with your people at your table.
Four variables.
Yeah.
Oh, yeah. 0, 8 model parameters.
I think that's aren't you always gonna have one?
Unless you have one.
But why is it 0?
Because you fixed it once. So it's not, yeah, it's not an unknown.
So it is, it's
Did you get the same arrow? Is that what you got?
So 4 variables.
We have ones that change. Oh, okay.
It just makes sense in your paper out.
Because that was.
Let's go back to look at the model.
Yes. And then I run a check. Okay.
I'm the number.
Oh, no, I was doing the first one.
You got it? I got over.
Over.
It's no like an unknown.
Loading
So we had 10 known minus 8 unknown.
Move on to the left on top one. Wait. Left on top.
No, degrees of freedom.
Maybe go like that.
Degrees of freedom is 0 minus unknown. So we have 10 known minus 8 unknown. We do have to try this first.
That's bad. What's the deep one? It's so fun though.
I think the second one is nicer.
Like multiple times.
What's my sound? So they recognize this.
Yeah, fair. Why? I think it's not good. I've never eaten it. Always pull out stuff.
The first was the raisin.
Why are you just doing it often also? You were hard to eat so often.
I was trying to decide if it was chocolate or raisins or both.
Blueberries.
Oh, there's one I have blueberries.
Yeah, so is ours.
That's what I was really
That's
So it's like
Was it cinnamon or was it like
the truth.
something else? Brown powder. Dirt. Honestly, I don't know. That's why I couldn't figure out what it was.
Raise your hand when you all have both of them done. Okay, okay. Got it?
Yeah.
Okay. Okay, so this 4-item, 1-factor model, did you say it was over, just, or under identified? How many said over? Okay, just, under, okay. So we're all saying we think this one is over identified. We have 4 variables, so how many knowns do we have? 10. How many factor variances? 0, errors, and loadings. Okay, so this is 8. So what were the degrees of freedom? 2. 10 minus 8. Very good. And the next one, we just have 2 items. So we have 2 variables, which makes how many knowns? Just 3. Only no factor variances, 2 errors, and 2 loadings. So we have 4. And what was this one? Under identified, yes. So our degrees of freedom resulted in a negative number, which is like red flag, we can't have that, we can't have that. Okay, so the next ones actually have 2 factors. You can see here on slide 33, 34, and 35. And you'll note the different identifications that are on those. But in your tables, do these 2-factor models and determine their identification.
Then we have variance of factors. We have 4 errors, yes, 0, and we have 4 loading. Oh wait, 0. And then 1 is 4 loading. Down. 7, 8.
The variances are known, but the covariances.
Just do slide 33 and 34. We'll discuss 35.
Is that what you guys got?
I don't know.
So then this guy is still
variance.
These are variables. Ours are 57.
I think somehow yours didn't, it got deleted, but you also do want to include the covariance of the factor.
Okay.
It's on mine, I don't know why it got deleted off of yours.
Yeah.
How do we get 1 time?
Just over.
It's no minus 7.
This one is a power.
But if it's known minus unknown, that's what I'm not understanding, because our knowns are 10. Oh, okay, I get what you're saying. So, how many unknowns? Is 1.
We're on
So
slide
that's 9. So then it's 1.
Wait, why is the variance of factors? You've got 2 and 1.
We have 1 unknown covariance factor. So then it's 9, so 10 minus 9 is 1.
A lot of times we never assume. We don't have
I don't either, and I just use one.
She would do like covariance with that, but she would never do that.
Oh, are we supposed to do?
Just do slide 33 and 34. Raise your hand when you're done. So this one here, we have still 4 variables. So how many unique knowns do we have? 10. How many unknown variances of the factors do we have? 0. So notice that factor identification method is that all of the factors have a variance of 1. We wouldn't just fix one of them, so it's consistent across all of them. How many unknown covariances do we have? 1. So now we have this covariance that we are allowing to be estimated. Error variances, 4, and loadings, 4. So how many total unknowns? 9. Very good. And what is the degree of freedom? 1. So it is over-identified, and that's really good. We like it to be over-identified. The more knowns is greater than the unknowns. So what about this one? What is different if we still have 4 variables, 10 unique variances and covariances? What is different about this one? We don't have the covariance of the factors. So covariance, 0. How many factor variances? 0. Error variances, 4. And loadings, 4. So what are the degrees of freedom here? 2. And this one, it seems over-identified, right? But really, what is it? It's actually, it seems over-identified, but actually, it's 2 one-factor models and we did that one where we have 1 factor and 2 variables here, and we said it was under-identified, that are under-identified. But it's true, it does seem to be over-identified, but it's actually 2 under-identified structures. So just something to be aware of, because really we could say, you know, if I wanted on the path to put this in, I would say C12 equals 0. And that's a specification that we can make in our model whenever we put it in, that we think that, kind of like oblique or orthogonal, we think that these are uncorrelated. So we're fixing that. The last one here, not a whole lot of difference, still 4 variables, 10 knowns, no factor variances. The covariances, 1, variance of errors, 4, and loadings, 4. So again, this one with 9 appears to be what? Over-identified. So it seems over-identified. But if C12 is freely estimated, then it's possible to be 0 or close to 0. In which case, we're back to that seems over-identified, but it's actually 2 unidentified variables. It's like if you're exploring the rotations and we don't know, well, why not run an oblique rotation and see if they are or they aren't, and then proceed with whatever that tells us. Here, we could allow that covariance to be estimated, but if they aren't related, if those 2 factors aren't related and we're including that, then it's trying to estimate something that really isn't in the data. And so that, again, is problematic. So all 3 of these 2-factor models actually appear to be over-identified and working models. But I just want you to be aware of, even though on paper and pencil, 1 + 1 does equal 2, what the actual data supports may or may not be identified. So just something to be aware of in that. So some recommendations for identification is that each factor must be assigned to a metric. Either fix the variance to 1 of all factors, if we have multiple factors in our model, or specify a reference indicator by fixing a loading to 1 from each factor. So on this one here, I gave you all examples of identifying in terms of the factor, but if we wanted to freely estimate this and call it C11 and C22, then we can fix lambda 11 to 1 and lambda 32 to 1. So we have to fix and identify one lambda per factor, or we have to specify the variance of all of the factors. So we also have to note that a model may seem to be identified, but locally or empirically, it could be under-identified if there is no correlation or we think there is and the data doesn't support that. So some other rules, there's a 3-indicator rule and there's a 2-indicator rule. So this 3-indicator rule by Bolin is a standard factor analytic model is identified if at least 3 measured variables are a function of each factor, and each measured variable is a function of exactly 1 factor. So again, each factor has at least 3 variables, and each variable is, it's like simple structure really, only associated with 1 factor. So for example, if there are 2 items and 1 factor, we don't even have to use this. If there are 2 items and 1 factor, does that meet the 3-indicator rule? No. If there are 3 items and 1 factor, would that meet the rule? Yes. And if there are 4 items and 1 factor, would that meet the rule? Yes. The minimum model for 2 factors, F1 and F2, would have to have at least how many items? 6. V1, V2, V3, 4, 5, and 6. So minimum would have to be this, and there could be no cross loadings. So maybe we have this and that. It could have been 1, 3, 6 and 2, 4, 5, but there are 2 subgroups of items for each of those. That's the 3-indicator rule. Bolin also has a 2-indicator rule for identification, where at least 2 measured variables are a function of each factor. So it lessens the number of variables per factor we need. Again, each measured variable is a function of exactly 1 factor, or again, simple structure. And each factor has at least 1 non-zero covariance with another factor. So back here, when we said this was a minimum for the 2 factor, I didn't specify a covariance. There may or there may not be a covariance. But if we don't have that many items and we have fewer items, then there must be some covariance between those 2 factors. So we should design our studies to avoid the problem of under-identification. For each factor, include at least 3 variables, or at least 2 variables that we believe strongly load on that. And to the extent that a factor may be thought to be uncorrelated with other factors, we need at least 3 measured factors, or measured variables. We could add measures that we think load on multiple factors, but these should be in addition to the minimum mentioned above. So there could have been, you know, maybe a V7 out here that went to both. But at minimum, what I drew earlier without that cross-loading has to be specified. And then unfortunately, we often don't know the relationship between the measures and the factors. So again, we're just trying to confirm based on a lot of theory and background and stuff that has been done, that's what's guiding. And that's why it's so important that it be guided by theory, because this idea of identification is really, really important in practice. So in summary, CFA can be framed as SEM, structural equation modeling, with latent variables. Latent variables as factors or constructs that are constructed by researchers as a way of explaining why measures covary. So sometimes SEM is thought of CFA, let me back up. CFA is sometimes thought about as SEM without the structural component of it. So it's the CFA plus the structural component makes SEM. That's kind of, in a nutshell, the difference. But do the data support an a priori theory that includes structural links from the factor to the variables? And we have these model implied variances and covariances rather than just an exploration. An identification involves arriving at a unique solution for each parameter. So you might think about the identification process much like we made constraints about our eigenvalues and eigenvectors back in EFA, and assigning each latent variable to a scale either by specifying the variance or the factor loading to equal 1. Okay. Questions? Do we need a break? I'm going to get in, this next part's kind of like the big chunk where we get into R and I'll work with some data. Do y'all want a break or are you good? Okay, a little break. Yep. Let's say 11:30.
Oh, yeah,
Do you
yeah.
want to see it?
Yeah,
Yeah,
I
I
get the double subscript.
No, I didn't. But
It looks nice. What are you gonna ask? I'm sure. I'm sorry. I mean,
Six, but it was just because of the table.
yeah.
Right.
They don't like go on.
And you kind of putting it together, like, I have like a whole one page, basically all this stuff. Like, I have like 2 samples of it right on the page, and I'm doing the tables, I just like scooted them down, like, so that they weren't broken and stuff.
I just remember that's what
Yeah.
it was.
So, and like,
What's that better? Oh, you can just like look down?
Yeah, that's like where you do like redo it. I didn't
Yeah.
make it.
Oh, wow.
Haven't
I'm
finished
sorry.
it.
yeah, do it really.
Maybe I'll just have an opportunity. Well, because we have
Right.
3 independent variables. The
Or
other,
like how many points.
the example table only had 1, and I was like,
Also, like,
oh, I just have to have 3 sections.
I just feel like that.
A whole page. Mo did not message me back.
Did Misty ever reply to that text that was about what that balance would happen? Yeah. After you left, like, it was like highlighted.
Well, he also had like a textbook, so I thought maybe they were in a class. Like they were like taking this other class.
oh,
She told me I was this unique bird or something.
yeah.
Rare bird,
Oh,
especially in these ocean environments. She just typed environments. Already double pocket points today. You need to download it.
Okay.
Except for
Nobody
June.
uses
I mean, I
it
kind of
anymore.
figured that might happen.
They don't?
Not really.
We just went to Blues Cruise, and they had a BOGO,
Black
Friday,
Friday
like
by
small. Well, Sonic got out of it, Chili's got out of it, Wendy's got out of it. Oh. And, well, I know that, High Five, for 50 points, does BOGO, like, a whole pizza, 2 whole pizzas for like $8.
That's gonna suck.
Yeah, Buffalo Wild Wings got out of it. Oh, I don't go to any of those places.
Yes, you do.
Chili's and Buffalo Wild Wings? I lived here for a year and I've been to both of those places once.
I think both of me. 'Cause I like
Both of you, because you like them, exactly.
We used to have, we used to,
What am I doing?
I don't know, and I love my event.
Dr. Cole,
Mhm.
will we have, some time on Thursday to go down to the lab and work on stuff?
Yeah, probably a majority.
Oh, no. I did the. Here for 2 years and.
I think the way that I was thinking about it is like, that's why I just identified number
I don't know. I'm just afraid.
Okay, so we will pick back up and talk about this all in the context of an actual example now. These, again, are the processes for CFA. And so we need to think about, I need to talk about, rather, this part right here in the model fit statistics before we actually kind of jump into it. So this is the flow chart for once we do this, re-estimate the covariance matrix, compare it to the original, we get these different fit indices. So how does the fitted model compare to the one in which the variables were uncorrelated? So a CFI and TFI values greater than 0.95 are good. And then we get this RMSEA, and this is an error. So root mean square error. So if we see the word error, are we going to want a big number or a little number? A little number. So typically a value 0.05 is, or smaller is good. And so this is the root mean square error. So the error in the observed and the reproduced correlation matrix, squaring the values, averaging them, taking the square root. And those are the values that we get from that. This is the mean square residual. And so again, do we want residuals that are small or large? Small, And so our criteria there is less than 0.08. So these are kind of the things that you want to look at in terms of evaluating. And some of them might meet, some of them won't meet. You might have good CFI and your RMSEA is 0.09. And so there is a bit of subjectivity in evaluating these, but at least there's a bit more structure in terms of assessing the overall fit. So the gambling research instrument is something that we're going to use for the application here. This was all acquired from Templin in how he teaches the CFA stuff and gathering the data and all of that. So in the past 25 years, and this is real data, so that's kind of fun, has been an exponential increase in the accessibility of gambling. Hence, there's a need to better understand the underlying causes of gambling, specifically as a disorder, reliably identifying potential pathological gamblers, which is kind of like what we do with any scale. We need a lot of responses to make sure that it's a good scale, to validate it, to see that underlying structure. But then probably how we're going to use it is we're going to give it to one person and calculate that score for one person and see where they fall on this scale of stress or depression or whatever that might be. And then provide effective treatment intervention. So this one's specifically for gambling. So in order to study this, more variability in responses was needed. They had a gambling instrument, and it had 41 items using a 6-point Likert type scale. So the instrument was used on a sample of experienced gamblers from a riverboat casino in a flat Midwestern state. I'll let you guess where casino patrons were solicited after playing roulette, and from college students at that within that same state. So this is kind of a little bit of a vague background of where I'm coming from. So this instrument, again, initially had 41 items. We're not going to deal with all 41 items. But the items themselves were like, I would like to cut back on my gambling. There are a few things I would rather do than gamble. If I lost a lot of money, I would be more likely to want to play again. I enjoy talking about experiences. I find it necessary to gamble with a large amount of money. et cetera, et cetera, et cetera. And so the instrument itself and the data were acquired from these two different sources. So just looking at the first 5 items, that's what we're going to work with today. Tomorrow we'll work with a larger portion of this data set. This is the correlation matrix and descriptive statistics. And this is like a format that's often reported even in the structure, where we have the correlation of the different items, and then at the bottom we have the means and the standard deviations of the different items. So in this case, I would like to cut back on my gambling. Where on this scale, smaller numbers or larger numbers, would you say is a healthy approach to gambling versus a more an addictive behavior?
Larger would be healthier.
Larger is probably going to be better, and small numbers are going to be poor gambling habits. So that we always need to look at that, and whenever we go to evaluate means and standard means, especially of item responses, to know what do those averages imply. So from the data that we gathered, look, most of them are between 1 and 2. So, and this was from a big portion of gamblers and from college students. So just puts it into a little bit more perspective of what we're dealing with. So how well do these 5 items measure the construct of pathological gambler? And we have a 1-factor linear regression models from the 5 items. And so again, here you'll see it's a 1-factor model. And the 5 item responses are V1 through V5. So that's something that we've seen in terms of what does a CFA model look like. Now for the model identification. As it stands, we don't have any identified pieces yet, but how many variables are there? 5. And then how many unique known variances and covariances are there? 15. Good. Okay. How many unknown variances of the factors is there?
1.
Just 1, and there's not any covariance because it's a 1-factor model. How many error variances are there?
5.
5. And how many loadings are there? 5. So how many total unknowns are there? 11. So in this case, is it over, under, or just identified?
Over.
Over. What are the degrees of freedom? Good. 15 minus 11 equals 4. Good. And so this is the reproduced variance covariance matrix of those 5 item responses, taking into account the factor loadings, the variance of that single factor, and the errors of the variables. Okay. So I put each of the steps on the slide, then I'll bring up the actual program and show you no, let me pull up the program. Okay, so I showed you a little bit of our output last time and just at least exposed you to the syntax. So just start from the very beginning. Let's say you're at home and you want to try this on your own, which is another great reason though, like art. You don't have to VLab in, you work directly off of your own computer, your own drive that you want to. So here I've included this link in the today, day 7. Let me make sure that I have audio on here. That would be bad. Okay. And then use this link. It's going to take you to this CRAN project, and you will download the R 3.4.1, and it's real. Just use the defaults, click through all of it. It doesn't take up a whole lot of room. there's a lot of updates to R, but then you'll click on it and it'll execute and install it. So it's already been done on this computer because I don't have all the admin rights, so they came and did it for us. When you get R open, it's going to say this, and it's funny if you get into it and you've used it for a long time, because every time they change the name. And so now we are kite-eating tree. I don't know who comes up with these things, but each one has their own name. So this is what it looks like. Whenever you see a red little hat over here on the left, that's a good sign for you. You can type in there. So I could type, what is 1 + 1, and push enter, and it tells me 2. I can store a variable. So maybe I want X to be the variable, and when I assign a variable with a specific number, then we use the back arrow with a dash so that it looks like an arrow. It's like equal, and you can use equal, but it's not protocol for R. So I would use this arrow thing. So we might want to say X equals, give me a number. 5. Okay? And I push enter, and it looks, I don't know why that's purple. It looks like it didn't do anything, but in the background, it stored this variable. So now if I push X, what is X? X is 5. And I could say, well, what is X + 2? And what should that be? 7. And I could say, what is 2 times X? And that should be 10. Okay? So it's going to do all the very basic things. There is a, do they put it on here? There's a base package that is downloaded with R. And so it will do all of this multiplication, division, matrix algebra stuff. Like when I was making your slides and having to do a lot of the matrix algebra, I would input a matrix in here and use it to verify and do the matrix algebra stuff. So that's what it does. And then what we are going to work off, though, is what I call a script. Okay, so think of it like Notepad. So we're going to start a new script, and it looks empty. And over here, because whenever I exit, this is, all this is going to go away, pretty much. You can save it, but I don't really recommend that. But if I want to be able to open this back up tomorrow and already know what was X, what did I do with the code or the syntax, maybe I'd want to type it here. And so X was 5, and then I did something like X + 2, and I did 2 times X, okay? So this is my syntax, and I can save it. And I'm going to save it maybe just on the desktop and call it our syntax. You call it whatever you want to. And then if I go to my desktop, here it is, our syntax. But it is an R file. So you can open it up with Notepad. But when you open it up with Word, it doesn't upload that easily. So I would recommend Notepad. But it's here, and it's saved. And so we can highlight and right-click to run the line or push Control-R. I'll usually just push Control-R, and it will run that line itself. And then I could see where my cursor is. I can push Control-R, and it does X + 2. And I can push Control-R, and it will execute whatever is on that line. Okay? So I want to specifically talk about CFA. So we are taking like R 1.0 and now jumping to maybe R like 5.0. There's a big gap, okay? I would encourage you, if you want to know more about R, the data carpentry team through the library, they actually do R workshops. They're in the middle of one right now. So they do half-day workshops. They're like 9 to noon on Fridays sometimes. They had one last Friday. I'm teaching this Friday. If you want to know more about R or the computer software side of it, they do one on Python and SQL, all different things. It's more of a computer sciencey thing. But there are, because a lot of different fields use R or different software. There's somebody in there from plant pathology and from engineering and from ecology. All these people are using R and the different things, and it's used in the same way. So right now there's not usually people who come from the College of Ed or this field, so I would encourage you to go and show your face there. But if you open up in CFA folder and scroll down, there is a CFA and R, and it says it's an R file. So I downloaded it here, and then I can open and go to my downloads and click on the CFA in R that's in your Brightspace and open it, and you have all the syntax. It used to make you type it all out by hand, and I don't do that anymore. But I hope that you understand what it looks like. And so it does look very scripted, but I said R works through packages. So if it downloaded every possible type of analysis that it would do, it would be like as big as SPSS and SAS and those really huge programs that I don't know if you've ever put one on your computer, but it takes up so much space. R isn't like that. So you download it, it's real small, and then you just add what you need, and it builds up. So this first one that you're going to use for CFA, it's called the Levon package. And the way that we put it on our computer is through this function. So a function is where we tell it to do something, and in parentheses, we specify what we're telling it. So I'm telling R here to install a package, and R is going to say which package, and in quotation marks, I say Levon. If I execute this line by pushing Control R, that's because I'm not an admin, but maybe it'll still work. Yes. Okay. It will always do this the first time you install. The first time that you use a package, you have to install it. But once it's on your computer, you don't have to install it again and again and again and again. It will always be there. Here you pick your Cranmere. Sometimes just for the fun of it, I act like I'm in Ireland or Iceland. But we should go to a USA. It's just the window that it's using. There's a lot more technicality to that, but these are everything that it's downloaded. So download. You'll get an error if it doesn't, but as long as it looks good, you don't see any errors, then it did install it. It's installed on your computer now, so that you only have to do it once, but then you have to load that package, and we do that with the function library and Levon. So then you will execute that line. It will give you a warning, so just be aware, but it shouldn't hurt anything. Now, something about R is that it's an open source resource. So what does that mean? It means that I could build a package, and I could call it the Kykol package. I could upload it to the system, and I could say it does this and this and this and this, and then you could go home, install that package, and use it. Now, the way that you use it and if it's correct or not depends on how I wrote it, right? And so you're just trusting that me as the developer knew what I was doing and made a good package. But it says, please report any bugs, okay? And not all of the packages will give you this. The well-established ones are all great, and most of them are really good, but you do have to be careful whenever you use these different packages. Sometimes they do have errors in them, and I've often emailed the developer and say, hey, I'm getting this, or what's happening here, and they're really good about corresponding and writing you back if you have a question about it or something like that. But just do be careful because it is open. But Levon is good. It was built really well. Okay, so what next here? What do you need to know about R? Okay. Typically, you can read in a lot of different structures. You can read in a text file. You can read a CSV. You can just input the data itself through some code. But I usually will import CSVs. You can import Excel worksheets or spreadsheets as well, but this to me is the easiest. So let's see. Read.csv is the function to read in the file. my file is stored on my little USB stick in this folder called Factor Analysis, Data, Gambling, CSV. In your Brightspace, you have a gambling CSV. So you put it wherever you want to, and then in your code, you would change all of this portion here to be wherever you specify your downloads or some drive. Here, this NA.strings, I'm just specifying what a missing value is. So in this case, it's just a dot. And then over here, I have what is the number sign, and now when I see it, I think hashtag. So you can think hashtag comment. Anything that is past the number sign is a comment to R, and it won't execute anything past that. So this just says note. Data files with missing noted by dot need option NA.string. Yeah.
There's a function, I forgot what it was, but how do you search for a CSV file that you put somewhere? Like if you're not apt enough to name the locale of where you saved your file, isn't there a function under read.csv to search your computer for that? And you double click the file and it opens.
I don't know a function in R. I do know like mine is in
And downloads are on your stick name?
Yeah, so on my stick, if I'm like, wow, that's really long, I don't know how to put it in. Data, gambling CSV. You can right click up here and copy your address from where you are up here. I'm not sure, how does it script it? Okay, so it puts it in like this, and it would input that, which is great, but notice the direction of the dash compared to my direction of the dash. So you would have to go in and change that. I don't know how to do that directly in R, though. If you find out, let me know. Okay, so I could just highlight, and I just want to run a portion of this. If I highlight and just run that selection, then, whoa, look what it does. Over here, I just have a lot. This is what the data looked like. The last variables were G40, G41, but I don't want to see everything. I want to store all of that data into a variable name, and so that's what I've done here. Data equal, and you could use the arrow if you want to. But if I run this line where data equals read CSV, it looks like it didn't do anything, but it actually stored it as the data. So if you have a large data set, this is the way to handle it in R. So now if I see head, function head data, then it will print out the first 6 rows of your data. So you can see what it is without having to look at the 41 by 1300 spreadsheet and looking over all of it. It's good to observe, okay, yes, the values are going from 1 to 6. That's what we had expected. We could ask, what are the dimensions of the data here? And it has 1,328 rows and 41 columns, because originally this was a 41 item scale. Okay, so that's all of the data. If I just want to know and deal with the first 5 columns of the data, then I could use this specification here of brackets. So data bracket, what rows do I want? So maybe I want, let me do it this way. Maybe I just want to overview the data, and I want to look at the first 6 rows and the first 5 columns. So in brackets, I specify the rows and the columns that I want, and then it would output for me the first 5 columns and the first 6 rows. If I want to know, well, what is the value of data for person 22 on item 5, then it would give me that person responded 1. They strongly agreed. I don't remember which direction it was. But it's row, comma, column for the data specification within brackets for a matrix object. Okay? So what R works off of is the covariance matrix of the data set. And so today we're just working with the first 5 items. So everywhere here you will see data 1 through 5. So COV is the function for calculate the covariance. So if I run this line, again, you can highlight, right click, Control R. Here is the covariance and the variance of the data. So the variance of G1, G2, G3, G4, G5, and then the covariance of G1 and G2, G1 and G3, so on and so forth. This is the goal, is to specify this CFA model and try to reproduce this CFA model, and that's how it's going to calculate the residuals and things like that. Okay, are you with me so far? Good. Okay, so in the PowerPoint, what I have walked you through is that portion of the code where we installed our package. We only have to do that once on a computer. And then we library to load it, and you'll have to load or library every time you close and open R. And then the data is stored using this function read CSV. And then we could look at the first 6 lines, the dimension, the covariance, or the correlation. And I specified data columns 1 through 5 because I'm specifically going to work with the first 5 columns today. Okay, so the rest of the R syntax is here. I've copied it into PowerPoint though, so we could talk about it in a little bit more detail, and then I'll go back to R. First, we're going to do this using the marker identification. And so here, again, everywhere you see the number sign, that's a comment. And I encourage you, put comments in your code to remind yourself what you're doing, okay? So I say model 01.syntax equals. So this starts the model specification. Everything I do after this is being assigned to model 01. This is the first one. And so the first thing that we want to put into this is the factor specification statement. And it's actually the only statement needed, but I want to give you a few other pieces of that. So I'm saying gambling equals tilde G1, G2, G3, G4 plus G5. That's how we specify any of the models. So it's always the factor name, I'm calling it gambling, equal tilde, and then the names of items. So remember, in the head of the data, the items were called G1, G2, G3. You might have called your items I1, I2, I3. Whatever your item name is what you want to specify in the G1, G2, G3 location of the code. If you did regression in R, maybe you would have just done dependent variable tilde, the sum of independent variables. So a single tilde is regression, 2 tildes is variance or covariance, this equal tilde is the CFA modeling. And this is the default method. So by default, R identifies the model by setting the loading of the first item after the equal tilde equal to 1. I'll show you how to do the other method in a bit. So again, that's all that you actually need for the model specification. But some other things that we just constrain by default in order for the identification to happen is that the factor means equals 0. So remember, we said the factor had a normal distribution with a mean of 0. This is how, if you think, no, I actually want to scale it to have a mean of 1 or a mean of 100, this is where that would be changed, but you won't do that. And then the factor variance, right now, if I specify the first factor loading to be 1, then the factor variance is freely estimated. So here, gambling tilde tilde says it's free to be estimated. If you wanted it to be 1, you would change that to 1. So these are outcome indicator variables for the intercepts. Again, not needed, but we could apply intercepts of 1 because think about we're taking all the variables and we're standardizing them and then we're evaluating everything. So in a standardized form, the average is 1. And again, not needed, but just as part of the model itself and so that we can see all those different paths, the loading, the variances, the covariances, how are they input? These are the unique variances, those error components of the different variables. And then I'll highlight this last quotation mark because the model was specified between the 2 quotation marks. That's open the model, close the model. Notice in the model, we haven't even referenced the data yet. I'm just setting it up first. Okay? So then after the model was specified, the model was called Model 01 syntax. And then I used that Model 01 syntax in the CFA function. So this is now actually put that data to that model. So the model estimation, the Levon, I think it's in Levon. It does have an SEM call, but we'll use CFA because we are doing CFA. And this is the function. And then the model that we specified goes into the function, comma. And the next part is the data. So we have data equals, and then here we just put whatever data it is that we want to fit to that CFA model. If I wanted all of it, because I specified here. So this is what I called the data variable name. We could have called that gambling data, and then here I would have to put gambling data right here. Okay, so whatever you name the data, and I just name it data, is what you put right there. And I just want to work with the first 5 columns. And then comma. And this other part, you just do this. Mimic M+. So you can do this in M+. I think the code is a little bit simpler. But if you're more familiar with M+, maybe it's not. And then there are different estimators that you can use to fit the CFA model. Will you just use that MLR? Again, you could also use the SEM function, but we'll use the CFA function.
You might have said this, but is there a character limit? Like, you know, in M+, it cuts you off after, like, it's not like that,
no? No, and everything in terms of naming objects in R, there's a lot of flexibility, but it's also case sensitive. So here I called it data. That would be very different than calling it data. 2 different objects. So we have to be careful there. Also, you'll notice that, I'm not sure how it is in my R code, but I put multiple lines here. And so R can read multiple lines. We don't have to put one line that like way runs off of our screen and then we have to go back and forth and it's hard to read. We can put different specifications on different lines. It just knows after this function, you have an open parenthesis and it's going to keep waiting for more code and more code until it gets a closed parentheses, and then it executes. Okay, so we have to first input the data, then we have to specify the model, then we have to fit the model with the data, and then we have to evaluate the model. So the funny thing is we do this call right here, and think about all of the math and structuring that goes on in the background. This huge data set is trying to fit it, it's doing all these estimations, and it literally gives us nothing. We get that little carrot hat that's like, I'm done. And so we have to ask for the details or for the results, and there's different ways to do that. One of the functions is called summary. And this says, give me a summary of Model 01 fit. So let me point out a specification here. This is Model 01 syntax. And then I put that syntax into fitting the model, and I called it Model 01 fit. So these are just object names. I could have named them anything. Oh. But I want to specify that the Model 01.syntax is a different object than Model 01 fit. We use the fit to get the results because that's where it stored all of that model fit stuff. So this is just something we want standardized. Another one is called fitted, and another one is called code, because that's what we are trying to specify. We could also inspect, and I'll show you in the output what all those different functions actually give us in the output, okay? But I want to show you in R what I'm doing. So if I open up R, okay, here you see the Model 01.syntax, quotation mark, and if all I do is run that single line, notice I don't have the carrot hat anymore. I have a plus, and this is R saying I need more. You opened a quote, but you didn't close it. You opened a parentheses, but you didn't close it. I need more. So I could run a blank line. It still wants more. I run my comment. It still wants more. I run this gambling line, and it's going to keep wanting more, and I'm going to keep outputting and sending it that syntax. But notice once it closes the quote, I get my carrot. Okay? If you didn't want all of that, I could have just ran Model 01 syntax and gone through and just specified the lines that I wanted. If you wanted to, do it a little cleaner. Everybody has their own method of input. It doesn't really matter to me. But this is your indicator that, okay, I have syntax. The next is the model estimation. So I'm just going to run the CFA one. I could also, let me put it like this so you can see it. If I just run the first line, it says, okay, I know I'm fitting a CFA function, but you opened a parentheses and you haven't closed it. I still haven't. Now that it's closed, you saw that slight delay, like millisecond, and then it's done. Okay. Now we have our syntax, we have our fit. If we summary the model fit here, and I get all this output here. I'll talk about it in detail. I just want to show it to you. A lot of output, though. Some stuff that, oh, that looks familiar. So it used the Levon package. It converged. It still does that iteration process like EFA, and it took 21 iterations. There were 1,328 observations. And it gives a lot of model fit statistics, but we'll just point out and pick out the ones that we want. So from the ML estimation, we have a chi-square p-value, Oh, there's a CFI and a TLI. And here is an AIC and a BIC. And then an RMSEA and an SRMR. That's all model fit information. After that are the parameter estimates. So here we have the latent variables. These are the observed variables themselves. The average of the gambling. Why is that 1? We fixed it to 1. That was the identification process that was set. Was that lambda 1, 1 equaled 1. Here are our other latent variables. Here are the intercepts and the variances of the different variables. Then we have fitted. This is the fitted covariance and mean of the data. And then this is the actual variance and covariance of the data. So we could compare those visually and see what is the CFA model fitted compared to what actually was true from the data. And then the last one that I'll talk about is this inspect function, and it's an R squared, and I'll talk about what that means. Okay, back to, here is the first set of outputs. So model fit statistics. The CFI and the TFI, I think, was it you pointed out that actually R in EFA gave us that Tucker index? I think that's what it was. And so it gave us that index in even EFA, but we'll use it specifically here in CFA. Compared to fit indices, acceptable values are greater than 0.95. We want it as close to 1 as possible. So in this evaluation of the CFI and the TLI, we've already encountered, we met it for one and we didn't meet it for the other. This happens so consistently. But overall, they're pretty high, right? Okay, so overall, let's see, 0.97 and 0.94. So we're going to say okay. The AIC and BIC, these reflect the extent to which the observed and predicted covariance differ, but this one is used to compare multiple models. So I'm not comparing this fit to another model fit, so I'm not going to really use the AIC or BIC just for this single fit. Then the RMSEA, we want it low because it's an error. We want it less than 0.05 if possible. And where did we get to? Oh, we're close, 0.06. And then the standardized root mean square error of the residual. Again, a residual, we want it small, less than 0.08. SRMR. And where do we see it at? 0.024. And that one we would say is good. So overall, I would say our model is good. If at this point we said, ooh, we didn't meet any of those criteria, stop. Don't go to the next output, start looking at the estimates or anything like that, because the estimates don't really mean anything.
Did not do the chi-square one?
I probably, oh, here it is. Yeah, okay, there's the chi-square up there. Okay, so the estimates are the unstandardized factor loadings. Here we have G1 through G5, and the dependent variable, we called it gambling. So think linear regression. We might say y equal beta naught plus beta 1x. And in the unstandardized form, that slope is the unit of y over the unit of x, change in y over change in x. So the first factor loading is 1 with no standard deviation or no standard error. So there's nothing here. That's what this is, because it's fixed for identification. So for every 1 unit increase in the factor of gambling, or whatever y is, we expect the item response to increase 1 point for G1, 1.246 for G2, 0.741 for G3, so on and so forth. And these are the estimates. Then the estimates are, we can take the estimates, and then we have these standardized values, which are calculated by taking the unstandardized value and multiplying it by the square root of x. And STD all is fully standardized. So we have partial, and then we have fully standardized values here. Any of them can be reported. Just be careful to specify the units that you're using. So over here, when we're talking about the estimate itself, we're talking about actual item response units. And once you standardize it, you kind of get rid of those units themselves. The estimates, the partially standardized, so G unstandardized multiplied by the square root of x, or f in this case. So for the first one, we have 1 multiplied by, if we look at the corresponding variance, 0.371, 1 times the square root of 0.371. Somebody calculate that, see what we get. Bring your calculators or your phones, because I know your phones have calculators on them.
0.609.
0.609. And what do we see that the partial loading of that item is? So if we take the latent variable raw estimate and multiply it by the square root of the variance of the factor, not the variance of the item, but the variance, notice this was the variance of gambling, of the factor itself. Then we get those partial standardized loadings. And then for the full standardized, when the values are fully standardized, if we're thinking about building up that formula, then we could take the latent variable squared plus the variance, and that should equal 1 of the individual items. So for the first item, we could take the latent variable estimate, 0.597, and square it, and add, what's the variance of the first item?
1.
That is of the dependent variable. What about the first item? 0.643. What does that equal? Put that in your calculator. .9999. Yeah. So it's 1. The same thing for variable 2. If we take the standardized estimate, 0.471, and square it, and add the variance of the second one, now 0.643, 778 should get one. So get that? Okay, good. So these are the different estimates that we have. What else do we know? The item intercepts are the means of the observed items. So we just did descriptive statistics of the first 5 items. Whoops, wrong button. Then we would get these averages for the 1,300 observations on the first 5 items. And notice the intercepts, initial estimates, not standardized or anything, are the same as the mean. They actually are the same for the partially standardized as well. So in the model specification, remember we set the mean of gambling to, does anybody remember what we set it to? 0, yeah. What line of code? That happened by default, but I showed you in the code where that was, right here. We set the factor mean score to 0. It would have done that by default. Again, we didn't have to run those additional lines, but that's where we see it in the actual output here. Okay, so we have item parameters. Then what about the variances? So the factor and item variances are those unique variances that we see there. So latent variables, intercepts, and variances. Now, we didn't observe the latent factor of gambling. That's what we're trying to estimate. But we expect the distribution to be normal with a mean of 0 and a variance of that unknown factor to be 0.371. Because we are using the marker identification. So in this case, the intercept of the first variable is, or the first latent variable is 1, and the variance was freely estimated. If we would have fixed the variance of the factor to be 1, then it would have freely estimated the first factor loading. But we can use this to estimate the 95 percentile, so make that confidence interval of the score for gambling. So if we take the average mean U plus z-score for the 95th percentile, 1.96, multiplied by the square root, then we could construct this confidence interval for the low and the high. So 95% of people have a gambling score between lower bound and upper bound. So how do all of these different components fit with the model equations? So here is the model equation that we're trying to estimate, and all we knew to start with was the matrix B, the actual data. And then we have the means, the factor loadings, a factor score, and the error components. And these are the different parts. So this first set is the matrix of factor loadings. The second set of intercepts, let's see, starting here, these are the matrix of intercepts or item means. And then this last set of variances is actually the diagonal matrix of the variance of the error components. So how well was it able to reproduce the correlation matrix? If we take each of those pieces from our lambdas and our variances then we could put them into this equation, and we're not going to do this by hand. But this is what R is doing in the background, estimated those things. It put it into this formula to try to reproduce that covariance matrix. So those second function calls of what was fitted and what is the true covariance. So this is the reproduced covariance matrix that you see here. And this was the true or the observed covariance matrix here. And so we can compare those things. Look how close they are. 1.041, 1.041, 0.592, no, 0.492, and 0.462. So it's pretty close. There is some error there, though. Let me show you a few other calls that I put here in R, or a few other functions. So these are path diagrams. And this one we need to install another package called SEM plot. So I will install that one. It's using the same grand mirror that we had originally selected. This one's kind of longer. Question.
It asked for, it asked me if I want to install sources, from sources the packages which need compilation. Do I, the command is either yes or no?
Usually I just said yes to anything on ARM, but I'm not sure.
Something from our studio, so I just had your things here, I just read it. And so I did install packages and asked me. You know, this is,
Yeah.
so yes.
Still installing. But we know if you've had SEM, you know that SEM paths can get a little bit complicated. And so that's what it's installing here to produce those. I'll just go on and I'll show you in a minute. Once it installs that package and we load that package, then we can call this function called SEM paths, where we input the fit. So we called it model 01 fit. And then these are just different specifications. Intercepts is true, residuals, yes, style, layout, rotation, etc., etc. You can just use those same defaults or play around with them if you want to. You can't usually say in R, you can't mess it up. You can always just reinstall it or rerun a model or re-specify an item or an object. So you can't really mess it up. But this path diagram, it looks, you know, like what we would have done. So here we have gambling as the factor, G1, 2, 3, 4, and 5 as the items. And so we specified that the mean is 0. And here we know that the variance of gambling factor is 0.37. And then we get all of the different lambdas or the paths here. We did the marker identification there. And then the different intercepts. So these are actually the means of means and variances of the path. So not yet were those the theta values. Okay, so questions so far about this? Okay, we could have also done the standardized factor identification. So what we just did was marker item identification. And here we let the factor variance was freely estimated. And by default, it specified the first lambda to equal 1. Over here is the standardized factor identification. So what is different? Here, I'm specifying, instead of tilde tilde gambling, it's just free. It's tilde tilde 1 times gambling to set the factor variance equal to 1. The other component that you'll want to add is this stv.lv equals true, and this standardizes the factor so that it is mean and standard deviation specifically equal to 1. But that's really the only difference. Let's see, does it change any of the model fit indices? Does it change the value of the CFI, TLI, anything like that? Nope. So no change in fit. What about the item parameter estimates? Does it change there? Yeah, so these are the lambdas. And if we think about this being the lambda matrix, if one time one of them is fixed to 1 and the next time it's free, it's going to affect all of them. So yes, it does change the lambdas, and this is the variance. So either this is 1 and this is free, or the variance of gambling is 1 and the first lambda is free. Those are just the two changes that are different in those estimates. However, that's the initial estimates. Look at the partial and fully standardized columns of the output. In the standardized world, did it change anything? Nope, it didn't change anything from the standardized values. And then in terms of the fit of the model, even though the estimates were different, standardized, they were the same, did it change the reproduced covariance matrix? No, no change. So inspect, the inspect function can be used to report the R-squared variance accounted for in each of the endogenous variables or dependent variables by the exogenous factors. But remember, the factors aren't really observed. This is the proportion of variance that the item has in common with the item. So you might think about communality. The more informative or reliable, the higher that these values are. So we could compare, this was from model, ID, and standardized factor. So we fit it once and twice. Notice that, again, which identification method that we choose does not change that inspect value at all. So remember from EFA, the factor loading squared or lambda squared equaled the variance accounted for in an item by the factor. So these are like communality. So the unique variance is unaccounted for. So R squared equals the squared standardized loading. So if I take the fully standardized value and square it, then I get the variance accounted for from that factor to that item. So again, think about communality in this case. Questions? Concerns? Okay. These are the two path diagrams. Again, the values themselves change only on the factor loadings, for I hope clear reasons on why those factor loadings change. Here we have 1 and the first one is free, whereas in the first model we specified lambda was 1 and that variance was free. So it adjusted some of the other factor loadings as well. If instead of, so here, well, here on what labels do we want. We specified the parameters. So these are the estimates, the initial parameters. But if we would specify standardized labeling, label with the standardized values, then it's like the last columns of the output where we get the actual standardized values. Okay? So then in reporting, what do you want to report from a CFA model? Obviously, I hope, the model fit statistics, the CFI, the TLI, the RMSEA, and some justification of these meet or these don't meet, or these are close or they're not close on why you're proceeding, if it is a good model fit. In terms of the CFA model parameters, factor means, factor variances, item intercept, unique variances, those things actually aren't usually interpreted, but the main piece is the factor loading. This is the key statistic of the analysis. Typically done through standardized, so that in the end, in the interpretation, it doesn't matter what type of identification that you used. And the path diagram. So those three things are going to be probably the most important when you go to report or read about this. Skip one, descriptive statistics, what is the model, fit indices, factor loading, naming them, your path diagram, etc. Okay. So there's one more article. Maybe we'll start with that article tomorrow, and then we'll jump back in. I'll review a little bit tomorrow, but there is like a new part 2 lecture that you'll see and want to print off for tomorrow. Has anybody printed that off? Y'all print that stuff off early? Okay, some people have. Okay. If I make any changes to it, then I'll upload what specific changes were made and bring a copy of it. But the one that's up should be good. I just haven't reviewed it yet. Okay, so that's all that I have. I hope that today you will go home and use R some. Tomorrow, a lot more applied. We kind of got the fundamentals out of the way. We'll play more with that gambling data, and I'll bring another one. If we have time tomorrow, we'll go to the lab. I'm not certain. Otherwise, we'll definitely have some good lab time on Thursday. Okay? So have a good afternoon.